that I'm putting together right now for the first lab in the Met 10 lab class. And if you don't remember, we are using the AMS Weather Investigations Manual for this class. And so this is the first lab of the quarter, Lab 1A, which covers air pressure. Now, before I begin, let me just say that I don't plan on doing videos like this for every single lab. If this class becomes an online class in the future, I might do that. But for right now, I'm just going to do it for this one because this particular lab ends up actually being a little bit tricky. Interestingly enough, I feel like they kind of put our feet to the fire very early on. But once you get the hang of it, it's actually some very useful stuff. So first off, let's talk about what air pressure is. Now, I'm sure most of you have probably heard the word air pressure at some point in your life. I'm sure you know what pressure is. It's a force that's being exerted on you. And that force is actually being caused by two things: mass and acceleration. Well, mass is, for the purpose of our class, mass is just another definition of weight. Now, weight actually is a force. And then the acceleration is gravity. So really, when we talk about pressure, we're actually talking about weight. And so pressure is the weight of the air above us. And that's really the key thing that you need to know about air pressure. And the way that this works is that, believe it or not, all of the air around you right now has mass, from the oxygen molecules, the nitrogen molecules, the water vapor molecules, and so on. All of them have mass. And so they exert a weight on you. Well, here at the surface of the Earth, the weight is the highest. Why? Because there's the most atmosphere above us. Now, as you rise in the atmosphere, you have less atmosphere above you. As a result, air pressure actually declines the higher up you go. That's why your ears pop when you drive up a mountain highway. So don't believe me, drive to Santa Cruz up California 17, and chances are between there and here, you are going to feel your ears pop. If that doesn't do it for you, go up Highway 35, Skyline Drive, or drive up 130 if you dare to. I don't. But as you get higher in the atmosphere, there's less pressure being exerted on you, and that's why your ears pop. However, pressure also changes from location to location. So it doesn't just change with elevation, it also changes horizontally from location to location. As a result, there are some places that have high pressure and other places that have low pressure. Now, why do we care about that? Well, high pressure represents air that's being weighed down a lot. Therefore, high pressure air usually sinks. And when you get sinking air, you can't get clouds, you don't get rain. High pressure usually means very calm weather. On the other hand, in low pressure, you have much lighter air. And as a result, air doesn't sink. Instead, air can rise. And this rising air then cools and condenses, forming clouds, and then you can get rain. So we really do care about where high pressure and low pressure are because we want to know where weather systems are and what the weather is going to be like. So the more we know about the pressure of the area, the more we can know about the weather in the area. Now, that's not just the first thing that you need to know. There's even more to it than that. But before we continue, today we're going to be looking at something called a surface pressure map. And something I should mention about surface pressure maps is that surface pressure maps are calibrated to sea level. Basically what we do is we take all of the elevations that are present on a weather map and all those pressure levels, we convert them to sea level. The reason why we do this is because air pressure changes with height. So just by logic, the air pressure at the bottom of a valley is going to be higher than the air pressure at the top of a mountain. However, the change in air pressure from the bottom of the valley to the top of the mountain might not be due to any actual weather event. It might not be due to the presence of a low pressure system or to the presence of some kind of other force that is causing that change. Therefore, we want to take out elevation influences. That way we can just focus on where high pressure and low pressure systems are present. And so what we do is we take all those values and we adjust them to sea level. And there's a pretty simple formula to do that. Down here near the surface of the Earth, it's approximately, if I recall, 10 millibars for every 100 feet, something like that. You don't need to know that. But that's a very simple equation. But what you do need to know is that all pressure calibrated to sea level. All right? Now, there are many ways that we measure air pressure. There are many units that we use. Similar to how dollars is one unit of money, whereas cents is another unit of money. Well, the units that we use for pressure are pounds per square inch. And believe it or not, right now you have about 14.7 pounds weighing down on every square inch of your body. We also measure it in inches of mercury, and that has to do with the original mercury barometer. But the way that scientists usually measure air pressure, and the unit that they usually use, is called the millibar. And that's what we're going to use here. Now, the millibar pressure range is usually from 950 to 1,050 millibars. And what that means is that at the surface of the Earth, pressure rarely is above 1,050 and rarely below 950. So that'll be more useful in the next few assignments that we do. But for right now, just know chances are it's going to be hovering somewhere between 950 and 1,050. All right? Now, with that said, we want to plot pressure on weather maps. And the reason why we want to do this is because without plotting it on weather maps, it's really hard to identify locations of high pressure and low pressure. Let me show you what I mean. Here's a weather map. And this weather map has air pressure values listed at different areas. But if I gave you some time to figure out where high pressure was located and where low pressure was located, it might take you a few minutes to figure out that, okay, the areas here inland look like they have slightly higher pressure. The areas over here near the coast look like they have somewhat lower pressure, and so on. So without isobars, we end up getting something that looks like this. It's really hard to pick out where high pressure and low pressure systems are. It's really hard to really diagnose weather patterns this way. A meteorologist isn't going to use a map like this. Instead, they're going to use a map like this. And this utilizes these blue lines called isobars. And an isobar is simply a line of constant pressure drawn on a map. And the purpose of this is it divides the areas that have higher pressure from the areas that have lower pressure. And once you plot a few of these on a map, you get a really good visualization of what pressure patterns look like. So going back to this, you can identify that, okay, over here, air pressures are a little bit lower. Right here we have a low pressure center, usually denoted with a bullseye. Meanwhile, areas around here, pressures are a little bit higher. And so this ends up actually being very useful to do that. Now, these are auto-generated isobars, and they usually end up kind of having some imperfections with them. The best way to create an isobar map is to actually do it by hand. And that's what we're going to be doing today. So in order to do that, there's a few rules that you need to know. And then once you know these rules, I'll walk you through a few steps, and then that'll be it. All right. So the first thing you need to know for drawing isobars is an isobar is like a line in the sand. It divides one thing from another. Everything on one side of the isobar is going to be lower pressures. Everything on the other side is going to be higher pressures. So for example, right here, I have this 1004 millibar isobar. And if you take a look, everything to the right of it is higher. You have 1005, 1007, 1006. Meanwhile, everything on the other side, on the left, is lower. 1002, 1000. This would actually be another isobar, but that's another story. Meanwhile, using that same map over here, what you actually notice is that this 1004 millibar line doesn't do the same thing. It doesn't divide lower from higher. Instead, there's 1002 that's lower over here that just so happened to be snuck on the other side. So this is an incorrect isobar. So when you're drawing your isobars, you want to make sure that you keep all of the higher values on one end, all of the lower values on the other end. And the trick that I'm going to say really quickly, though, is that it's not always going to be to the right or to the left. It could be, you could have lower isobars over here, or you could have higher isobars over here. You could also have a situation where you have 104 or 1004 isobar here, and then you might need that same one later on the map somewhere else. So that happens too. Now the next thing you need to know about isobars, though, is that we only do them for every fourth millibar. And there's a good reason for this. And that reason is if we did it for every single millibar, our maps would look a lot busier. There'd be way more stuff on there. There'd be information overload. And I don't know about you, information overload sometimes gets me and my head explodes. So the purpose of only doing every fourth millibar rather than every single millibar is to make the map look a little bit cleaner. Not only that, but since you're doing it for every fourth millibar, you can still infer pretty decent patterns. So for example, let's say this is the 1000 millibar isobar, and this is the 1004 millibar isobar. Everything in between those two isobars is going to have an air pressure between 1000 and 1004. And you could probably extrapolate pretty easily where the pressure is probably going to be 1001, 1002, 1003, and so on. Places very close to the 1000 millibar isobar are going to have air pressures that are closer to 1000 millibars. Places that are closer to 1004 are likely to have values closer to 1004. Places right in between are likely going to have values right in between. So we only plot every fourth isobar because that's enough to work with and it makes the map look a lot less busy. Now, what determines which isobars we use? Well, since we're doing every fourth, that means we're doing something for, we're only doing every fourth. Why don't we do numbers that are divisible by 4? So rather than doing 997, which is not divisible by 4, or 998, which is not divisible by 4, we're just going to do the numbers that if you divide them by 4, you still get a whole number. And so once you've got one isobar on the map, then just add 4 to the next isobar, or subtract 4 to the next isobar. So for example here, we have the 1000 millibar isobar, then the 1004 millibar isobar, and then the 1008 millibar isobar. If we were to continue drawing higher isobars, the next one would be 1012. The next one would be not 1014. Caught that just to make sure that you're awake. Not 1014. Nope. It would be 1016. It would be 1016, and then add 20, or then add 4 more: 1020, 1024, 1028, 1032, or you can also go back. 996, so subtract 4 from 1000. 996, 992, 988, 984, and so on. So we're doing it just for numbers that are divisible by 4, and this is actually the standard. Now, what this space between 1000 and 1004, this difference between the two, this is what we call an interval. This is called an interval, spelled INTERVAL. And that's just the difference, that's the space between the two. And the interval here is 4. The difference between 1004 and 1000 is 4. So the interval is 4. And so the interval with which we draw these isobars is 4. So now, the next tip for drawing isobars is when you draw isobars, chances are the pattern that they form is going to be very similar to the isobars adjacent to them. And that adjacent just means right next to. So for example, right here we have the 1020 millibar isobar. If I was a betting man, I would bet that the 1016 isobar is probably going to be shaped very similarly. Not perfect, but very similar. And then the next one is going to be shaped very similar to that, the 1012 millibar isobar. The one outside of that, the 1008 millibar isobar, and so on. And when you actually take a look, you can kind of see that, yeah, you end up getting very similar shapes to that initial isobar. So when you're drawing the next isobar, if you're ending up drawing something that is wildly different, then you're doing something wrong. A few other tips about isobars. Isobars don't just start and end on a map. Isobars actually do one of two things. They either go all the way to the edges of the map, meaning they continue off the map, or they close and form a circle. So they do one of those two things. They either go towards the edges of the map, or they close and form a circle. So you'll never see something where you have a map and there's an isobar that begins and ends on the map. It either forms a circle or it goes to the edges of the map. Another thing that isobars don't do is they don't branch out. They don't branch out. And there's a few reasons why, but just know that they don't branch out. One other thing that isobars don't do is they don't cross. Now this one kind of makes sense. So let's look over here. We have the 1028 millibar line and the 1032 millibar line. Well, if they were to intersect, if they were to cross each other, that means that at this point right here, the pressure would be both 1028 millibars and 1032 millibars. That's like saying that you weigh 100 pounds and 70 pounds at the same time. It doesn't work that way. You can't have two different weights at the same time. Your weight is your weight is your weight. It doesn't you can't have two completely different weights. It's the same. So you can't have two different pressures at the same time. Another way to look at this is go outside and ask yourself what temperature it is. Well, the temperature isn't going, or you can't have two temperatures at the same time. The temperature can't be 50 and 80. It's either 50 or it's 80. So they can't intersect. So they don't start and end in the middle of a map. They either go to the edges of the map or they form a complete circle. Doesn't have to be a perfect circle. They don't branch off and they don't cross. So they don't do those three things. And just to extend on that, isobars always close, forming a large circle. But you don't always get to see it. The reason why is because those isobars do continue on after they've reached the edges of your map. They go on to wherever is beyond the edges of your map. So let's say your map is for North America. Well, or let's just say it's just for the United States, just for the United States. Well, that pressure line, that isobar, does continue into Canada, and it does continue down into Mexico, even if Canada and Mexico are off the edges of your map. And they'll continue until they form a large circle. So let's say this is just a normal pressure map right here. So what I have right here, just a normal pressure map. Well, you don't always get to see the full circle. You could see something like this where here's the initial map. Meanwhile, somewhere else, that isobar continues and it goes all the way to the other side of the world, comes back around eventually, closing a complete circle. A few other tips about isobars. You can't skip isobars. So for example, I'll use a piece of paper here. For example, let's say you have two lines like this. Let me make myself a little bit bigger and see if that helps. Yeah, I can't make myself much bigger here. Oh well. So take a look, and you have 1,000 millibar isobar here, and 1,008 millibar isobar right here. Well, you can't skip the 1,004 millibar isobar. It's there. You have to include it. You have to include it. So you can't just skip isobars. The other thing that you can't do, let me move myself back up to the left. Up. There we go. The other thing you can't do is the other thing that you have to do is you have to label those isobars as well. You want to keep track of your isobars. If you don't label them, you don't know what they are. You don't know what pressure's doing as you cross those isobars. Is it getting higher? Is it getting lower? That's important too. The last thing is if you see your isobars forming what looks like a bullseye, well, that bullseye will actually represent either high pressure or low pressure. How do you know which is which? Well, this is why you want your isobars labeled. If as you're traveling to the center of that bullseye, your isobar values are decreasing, you are approaching an area of low pressure. Why? Because as you're approaching the center, isobars are going down, down, and down. On the other hand, if isobars are going up, up, and up, as you're approaching the center, you are entering an area of high pressure. So it's low pressure if they decrease towards the center, high pressure if they increase towards the center. Back to this. Now, The last thing I want to talk about before I do my demonstration is one other thing that we're going to be doing in this investigation right towards the end is looking at what are called pressure gradients. Pressure gradients are really important because they actually determine how strong the wind is. A pressure gradient is simply how great does the pressure change from one area to another. If the pressure changes very little, we have what's called a weak pressure gradient, a very low pressure gradient. In that case, pressures between one area and the next aren't that different. On the other hand, if the pressure changes substantially between one area and another area, that's what we call a high pressure gradient. In that case, the pressure changes substantially from one location to the other. Why do we care about this? Because it creates wind. Wind is actually caused by the difference in pressure. If the pressure change is great, that means that there's a big difference in the weight of the air, which is going to create a large wind, a very fast wind. On the other hand, if it's very small, you're going to have a very weak wind, a very slow wind. So, how do we determine what a pressure gradient is? Well, once you've drawn an isobar map, you can actually look at the isobars themselves. And those isobars will actually tell you whether the pressure gradient is high or not. Here's how. Excuse me. Whenever those isobars are really far apart, that means that the pressure isn't changing much over a large area. As a result, you have a weak pressure gradient, forgive me, and therefore you have a weak wind. So when those isobars are really far apart, that means very little change over a very large area. Therefore, you have a low pressure gradient, and therefore you're going to have very weak winds. On the other hand, if those lines are really close together, that means that traveling a small distance still causes a very big change in pressure. As a result, you have a high pressure gradient. In this case, the pressure changes substantially from one area to the next. This gives us high winds. So when the isobars are really close together, that's a big pressure gradient. When they're really far apart, that is a small pressure gradient. Let's do this really quickly before I show you really quickly how to draw isobars, and then that'll be it for us. So, this is a map of Hurricane Katrina, and each of these black lines here is an isobar. And as you can see, each isobar, they do break some of their rules here. They only dash the 1004 millibar isobar. They only dash the 996 isobar and so on. And I think they do that simply because the hurricane pressure changes so much between the center and the exterior. But let's not worry about that right now. Here's what you need to know. If you're far away from the hurricane, say here in Central Texas, the distance between one isobar and the next is very little. As a result, the wind between this area is also going to be very low. Why? Because the isobars are very far apart. On the other hand, if you're near the center of the hurricane, notice these lines are very close together. As a result, the winds are the strongest near the center, where these lines are really close together. So, just to recap on that, when they're really far apart, when these lines are really far apart, the winds are really weak. On the other hand, when they're really close together, the winds are really strong. Now let me quickly show you. Let's see if I can get this thing to grow. There we go. All right, let me quickly show you how to draw isobars. So this is a map, and this map is a little bit different than our lab assignment. This is actually last year's map. And basically what it is it gives you a bunch of different pressure values, and it tells you, okay, you are going to now draw the isobars. Now here's the thing. The AMS who made this already did us a favor, and they actually drew the 1004 and 1008 millibar isobars. So they drew those ones for us, so we don't have to do those. However, there's a lot of coverage here that we still have to do. So how are we going to do it? Well, if you've been doing this for a long time, and I've been doing this for about the last 10 years since I started my geography major, so that's a while ago. So I have some experience doing this. However, if you're somebody who doesn't have a lot of experience doing this, if you're somebody who doesn't really ever do this, or if you've never done this before, you might need more time to do this. So for me, I can just take a second and just sort of interpolate in my mind how to do it. Here's how I recommend you do it. The way I recommend that you do it is by finding places where you think the pressure is that value that you're going to be drawing for. So for this one, they want you to do 1004, 1008. The next one would be 1012. So look on this map and figure out where's the pressure going to be 1012. Now, in some places, such as down here in the Texas Panhandle, up here in Minnesota, and so on, the pressure is 1012. Well, what you want to do is in those places, put a dot right in the middle. So put a dot right in the middle. And at that point, the pressure is 1012. However, there's also a lot of spaces up over here where the pressure is not 1012. Instead, you may have on one end 1010 and on the next end 1014. In this case, you have to estimate where you think the pressure is 1012. So you have to estimate where it's going to be 1012. In this case, 1010 and 1014, I would assume it's going to be right in the middle of that. Right in the middle of that is where it's going to be. Why? Because 1012 is right in the middle of 1010 and 1014. It's halfway between those two. So you would probably put it right in the middle, which is what I did. Now going up further, right there, in this case, 1010 and 1016, in this case you would probably go, well, 1012 is a lot closer to 1010 than 1016, so you're going to draw the dot closer to 1010. Do the same thing up here for 1010 and 1015. Same thing between 1010 and 1014 right here. You would assume that they're probably in the middle. And then you would get a series of dots that look like what I've just drawn here. Once you've got those dots down, now we get to go back to second grade and do what everybody enjoyed doing, which was connecting the dots. So, using a pen of a different color, just connect those dots. And I'm going to do that right here. One second, I'll play some friendly elevator music while doing it. Do 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 do. And there you go. 1012 millibars. Now the next thing you want to make sure you do before you do the happy dance and say, yay, I did 1012, is you want to label it. So, labeled it 1012. Now, before you finish doing your happy dance, you have to realize that, well, now I've got to do 1,016. That's 4 more, that's the next one. So again, going to our map, let's put a red dot right where, right in the middle of the 10/16s. I'll do that right here. Got one there, one there, one there, and that's about it for right now. All right, so I found 3 places where it's 1,016. For everywhere else, we're going to, again, have to interpret where it's 1,016. We're going to have to guess, in a sense, where it's 1,016. So let's do that. So first, we have a place right here where everything on this side is closer to 1,012. Everything on this side is above 1,016. So I'm going to bet that there's probably a place right here where it's 1,016. If it's 1,012 here and 1,017 right here, 1,016 is going to be somewhere between those 2 points. And it's probably going to be somewhere closer to the 1,017. You could do the same thing right here between 1,014 and 1,018, right in between the 2. And then you could do the same thing. Let's take a look here. We got those 2, got that one, got that one. That one's there. Here's a good one, between 1,015 and 1,022. Between 1,015 and 1,022. Guarantee you 1,016 somewhere in there. Probably very close to the 1,015. So you're going to see something like that. And then another one between 1,014 and 1,020. Probably a little bit closer to the 1,014. And then there's another one up here between 1,012 and 1,019. And that's probably going to be a little bit closer to the 1,019. Probably not super closer. But then again, you get another series of pretty good looking dots. You have 1,016 down here. One right there. Another one interpreted right there. Another one interpreted there. Another one there. Another one there. There. And so on. And so you get this line of red dots. And again, just connect the dots. So we do that. And you're going to get something that looks like that. Make sure you label 1,016 again. And keep doing that. Do it again for 1,020. Do it again for 1,024. Do it again for 1,028. And so on. And eventually you're going to get something that looks like a complete isobar map. Now, there's definitely a few more tricks and turns to this, but this is definitely more than enough to get you through this first lab. If you have any questions while you're doing it, please feel free to ask me. Either raise your hand in class or shoot me an email. Otherwise, I think that's it for right now. Thank you for watching this. I'm Terrence Mullins, and thank you.